Oh, hey team. Hi, Zebra and Alias. It's good to see you guys. I started a little bit early. I had my tea is made, and I was just waiting for the clock to count down to when the broadcast was going to start. So I thought I'd just go ahead and start because it's like 5 minutes. So yeah, tonight we're gonna go through uh, a list of points that have been posted under, I think, all of my climate videos, if not all, the most of my climate videos, and then has now also been separately emailed to me. So I think that the individual that's been posting this is sort of looking for a response, maybe. So I thought that might be a good thing to do today. So I'll just respond here and yeah, just kind of do it all at once, all in one place. I have read through the arguments before briefly, but I haven't like really dug into them. So yeah, that'll be what we're doing tonight. But let's see, what is going on? Sunday's video that's going to go up, that's going to be, what's it called? Oh, okay. I sat down and went through what the climate and daily weather and what different weather patterns and things would probably be like in Barovia, which is a fantasy world out of D&D. It's where Curse of Strahd is set, and it's also the setting for the new campaign book that's coming out soon, Von Richten's Guide to Ravenloft. So I had fun doing some fantasy weather analysis. That video will be up on Sunday in lieu of my normal climate video. We're getting to the end of the semester for me, so like all my class projects are due soon, and I've had to do that instead of like write scripts. Yeah, sometimes when your day job gets in the way of doing the things you like. Yeah, there's a crazy snowstorm. You know what? Let's look at a quick weather map. Let me do that really fast while I keep chatting. I can show you guys the very cool Arctic pattern. Oh, the other thing, oh gosh, other things I'm doing that are, in my infinite spare time. Guys, it looks like I'm gonna DM, be the dungeon master for a streaming game. It's me, Gutsick Gibbon, her fiance, Dapper Dino, Chesh, TD Lane, Bent Hoven. So it's all the science friends. All the science friends are going to get together and play some D&D. So I've been writing a lot for that. So that's what else I've been doing with my time. Okay, let me share my screen and we'll take a look at the weather map. So what I look at, application window, we're gonna go here. So I prefer to look at, it's called like synoptic scale kind of stuff. And I do Arctic research. So these are the types of maps that I look at. So what this is, isn't that beautiful? This is potential temperature on the 2 PVU surface. That's the dynamic tropopause. So only weather nerds like me look at this, but it is kind of pretty and mesmerizing. Oh, we're going to stream to somebody else's channel, but I'm going to try to mirror them here so you can always find them here. We're going to stream on Chesh's channel right now is the plan. And we're still a couple weeks away because, like 3 of us are graduate students, so we're waiting for the semester to end. But I'm getting really pumped. We did our session 0 with like character creation and all that stuff. Okay. Anyway, so if we were going to look at this, today's the 21st. So let's step forward. 20. Okay. Here we go. So here's like today. So very simply, blues are like those dark blues. That's going to be, think of that as like Arctic air. And then the warmer the color, you see like over here, like off screen where it gets like deep dark red, that gets down to like tropical. And so this map is, we're staring down at the North Pole, right? So here's Alaska, Greenland, and so Toronto's in Canada. Oh my gosh, my geography is so bad. But you see this, we have this really sharp gradient with this deeply, deeply cold air aloft, and that even we get a deep cold tongue down over what that's going to be like Minnesota. Yep. And then further south down over the map. Yesterday, we didn't get snow, but like my parents did, and they're just a little northeast of us. So this is this unseasonal cold. It was a record cold day here in Oklahoma. And that has to do with this. We have this deep protruding cold air like aloft, and that helps generate these like cold fronts at the surface. And yeah, so this is a very wavy pattern. Wavy is a real science term, I promise. Oh, thanks, man. Yeah, no, just this is a polar stereographic map projection. That's a name I can just pull out of my butt. And Comrade Jerry, you're super welcome. I'm glad you liked my conversation with Kent. I'm also planning, I think, so he did a live stream on his channel like the next night, and I think he talked about the debate, and I think he talked about me a little bit. I might have hurt his feelings that I did if you haven't seen me and Dr. Josh doing a dramatic reading of an evolutionary, like a creationism chick track that we did for my 1K live stream. Strongly recommend. That was a hoot. But we were kind of poking fun at Kent a little bit in that. And I mean, like, if you're watching, Kent, feel free to make fun of me with my ridiculous unicorn hoodie. Yeah. Anyway. And yeah, okay. But yes, so the pattern we're looking at is a very wavy jet that is going to get us some unseasonably cold weather down here. But then also note that up in like parts of Alaska and other like northern parts of Canada, oh, that air is unseasonably warm. So you get these sort of like oscillations. I talked a little bit about this when I talked about the big ice storm down in Texas, and we got hit here as well. That the waviness of the jet can be, and this is, mind you, a very wavy jet. So a strong jet would make all that blue blobs more like a circle. And then the more perturbed it is, the wavier it is. And that can lead to bigger like weather swings and extremes across like the US. I mostly pay attention to the US because I live here. But bigger swings, and you would also see that over like Europe and Russia. Thank you. I love my unicorn hoodie. So and that a net weakening of the jet is in fact a symptom of a globally warming planet. Anyway, so yeah, let's take a look. Let me step through this so we can get an idea. This is also going to go into the forecast. So we're moving ahead in a 6-hour intervals of what the forecast is going to look like. So it looks like that cold tongue is going to kind of come back up. Oh goodness, that's a really interesting pattern. Look how warm, look at that warm air getting all the way up over the central Arctic. Like, that's astonishing. This guy, that's a big old surface cyclone, so you might get lots of precipitation, but that's over the ocean. Moving forward a little bit further. This, yeah, it looks, we might have some interesting weather in the next like week or so. But it doesn't look like they're forecasting having that big, like southern dipping tongue again. I could seriously watch this forever. It's just like watching a lava lamp. Ooh, look at that. Okay. Sorry, we'll put this away. I'll put away my toy. Absolutely, you answer the door in a unicorn hoodie. And okay, so cool. So we did a quick little check at the weather. It looks like it's probably gonna, as we move into May, I would be surprised if there was snow again, here in the Northern Hemisphere. Oh, hi, Scott. And oh, yeah. So yes, you had a warmest day of the year so far. That wacky Calgary weather. That is, you guys would have caught that like warm tongue and then the cold tongue. If you caught those like right next to each other, you would have had just crazy temperature changes. That's really cool. Okay. So let's take a look at the thing that I wanted to look at. Yes, the comment that keeps getting posted on my videos and emailed to me and things. Okay. So I copied it out of my email into like a Word doc. No, application window. Okay, we'll just share. I don't want to share my whole screen. I want to share this. There we go. I got to bring this over here. Okay. There we go. I'm going to share this. I just pasted it into a pages page. So yeah, all right. Team, here's what we got. Okay. So basically it's 3 arguments that this individual claims collectively are like the 3 legs of climate change and global warming. And supposedly these, the label here, leg 1, leg 2, leg 3, is debunking it. And then at the end, we've got a look at the Earth's energy budget, net energy budget. So we can chat about that. Okay, so this says, the radiative greenhouse effect theory, 3-legged stool toppled, together with all the pseudoscientific confirmation bias, correlation equals causation. Okay, so this is the claim that these 3 arguments are going to disprove all of this. Okay. So first of all, leg 1, by reflecting away 30% of the incoming solar radiation, the albedo, which would not exist without the atmosphere. So that this statement is not true. So let me just highlight it. So this is not true. I'll just make you red. Makes the Earth cooler, not warmer, much like the reflective panel behind a car's windshield. So albedo does reduce the amount of incoming solar radiation, which would cool the Earth. That is true. Remove the atmosphere and the albedo goes with it. So this is not true. And I'll explain all of this once I read through this paragraph. So this isn't real. I.e. no water vapor or clouds, no snow or ice, no vegetation, no oceans. The Earth becomes barren, airless, celestial rock. Okay, so got to be careful with all of this. Even if we took away the atmosphere, that doesn't mean you don't have ice or oceans. The atmosphere isn't what holds in the oceans, right? So that's not true. We'll just highlight all of this and highlight that in red. And much like the moon and Mercury, an albedo of 10% with 20% more incoming kilojoules per hour on the light side than the dark side, that's fine. And it's the moon and Mercury's, their albedo is set. I'll talk about that. Okay. Cool. UCLA diviner mission all tacitly admit the scenario. Okay. Cool. So now here's actually an issue right here. He actually says it. So the diviner mission, refuting greenhouse claim that the naked Earth. Okay, actually, I'm not quite sure what this sentence is supposed to mean. I thought he was saying here that like without the atmosphere, the Earth would be very cold. But he seems to also be saying that at the first he says that like the atmosphere makes the Earth cooler. So I think I'm not quite sure what this is trying to say. Without the atmosphere, I can tell you what Earth temperature would be. Um, um, Without the atmosphere, the Earth's temperature would be surface temperature would be 255 degrees Kelvin, which is about 0 degrees Fahrenheit. How do I know that, you asked? It's actually um, it's just the black body radiative equilibrium. And if that sounds complicated, I did a video on it. It's one of the first ones in my climate dynamics series where we talk about like, well, how do you know about what the temperature of a planet's surface should be based off of its distance from the star it's orbiting and how hot that star is, right? So it's not a completely accurate calculation, but that is how you would get the temperature. Like that's how you would find, you can calculate the black body radiation temperature of the moon. The moon doesn't have an atmosphere, so it really just is what comes in must go out. It's in radiative equilibrium. And so then that surface temperature is going to be the radiative equilibrium temperature. It's like, oh gosh, what is it? I think I can do it off the top of my head. It's the temperature to the fourth is equal to the square root. No, temperature to the fourth is equal to the Stefan-Boltzmann constant times like the solar constant. Yeah. Let me. I'm sorry, I got distracted by the chat. Pressurized atmosphere. So my guy. So the pressurized atmosphere, the fact that the atmosphere has pressure, what holds the atmosphere in place is gravity, right? So if this were truly a like pressurized system, like if we had a cap, then roughly the density of the air, right, in a column, so if you should be the same. So the air should be just as dense, just as much like oxygen at the surface as it is on the top of Mount Everest. So the thing that holds the atmosphere down is just gravity. Anywho, that's fine. Okay. I'm getting all distracted by chat, but that's okay. Okay, so all right, so the problems with those things that I highlighted in red. Okay, so albedo is just how shiny a surface is, right? Let's see. Mars has a very, very thin atmosphere. Um, uh, Mars has a very thin atmosphere, but its poles has dry ice, right? So CO2 ice is at the poles, both of its poles, and that's going to increase its albedo. So things that affect albedo is anything that's shiny. Here on Earth, the biggest effect we have of albedo is the ice at the poles. So the albedo at the poles is roughly twice what the global average is. And then the second thing that affects albedo the most is clouds. So it is true that one of the ways that the atmosphere sort of interacts with incoming solar radiation is to reflect some back to space, but that is certainly not the only thing that it does. So for example, let's say our atmosphere was like entirely carbon dioxide, right? It wouldn't really reflect a whole lot back to space, right? But that carbon dioxide would certainly interact with incoming solar radiation in a different way. You can just think about different. So the atmosphere isn't like one thing, right? It's made up of lots of different components, and all of those components interact with incoming solar radiation and then outgoing long wave radiation in different ways, and that is based on sort of their like absorption spectrum. So let's take a look at that real fast. I bet I can pull one up. So I'm going to open an incognito window, and we'll do. Let's just do like water vapor absorption EM spectrum. Okay. And I'm gonna share a different screen. I'm gonna share this one. Okay. Oh, that's super cool. Okay. Oh, yes, Carmine. Yes, I can't believe NASA flew a little helicopter on Mars. That was the coolest thing. Okay. Um, okay. I want to look for absorption bands and let's just pull up an image. Ah, brilliant. Look at this. Hey, this is perfect. This is exactly what I want to look at. Or did I click the wrong button? I might have. So this is what open image in new tab. That's what I want to do. Okay. So can we make in bigify? Okay. So team, if you're looking there on the x-axis, right, we see this is wavelengths of light. So from 10 nanometers all the way up to 10 millimeters. And notice they list it as like what range of light. So ultraviolet, visible, near eye infrared, mid infrared, far infrared, and then I can't quite read that, but that would be like getting into radio waves, very large wavelength things. So yeah, notice this is for water vapor, right? And so how much it absorbs. So when you put light of these different wavelengths and through a droplet of water, it absorbs almost no infrared light. Excuse me, not infrared. It absorbs almost no visible light. Visible light can just pass straight through a water droplet, no problem. It's how we make rainbows. But notice these lovely peaks in the IR, right? So especially like right there. And we do definitely have these like large values in ultraviolet. I'm trying to think of what exactly that refers to. Um, um, I'm wondering if that has to do with like, anyway, well, that's okay. So, but my point here is that when you look at a graph like this, right, you can see, oh, hey, water, and we can look at it for like CO2 and anything else you like. Water isn't going to absorb every single wavelength ubiquitously, right? They're selective in the wavelengths that they absorb. So we could look for the same type of image for carbon dioxide. Let's do carbon dioxide and absorption spectrum. Oh, this is like my favorite plot. I love this one. And this is great for what we're talking about today. This has to do with doubling CO2 in basic physics. Yeah, this is a good, all right. Open image in new tab. Okay, so I love this. So this is a plot of the downgoing solar radiation. So this is, and that's 70 to 75% transmitted. So what that means is of all the incoming light from the sun we get, 30% is reflected back to space. And this red curve, these red thing here, represents the light that makes it to Earth's surface. And then the blue is the outgoing radiation. And check it out. And then this is the x-axis here is by wavelength. So what we see, right, is this top gray graph here, this sucker. This is sort of looking at all of the gases of the atmosphere all as one. But look at carbon dioxide. So carbon dioxide is all the way over here, right, where we're getting that outgoing long wave radiation from the Earth's surface, and it cannot be bothered with incoming solar radiation. So if we're just thinking about CO2, and if we're just thinking about CO2, honestly, water vapor, notice we heavily peaks over here in the infrared with the outgoing long wave radiation. So if we're even just thinking about water vapor and CO2, they interact a lot more with the energy that comes out of the earth than the energy that's coming from the sun. Okay, so what does that mean in terms of our friends argument, right? So his argument was that if we that the atmosphere solely acts to cool the Earth, and if we took away the atmosphere, we would in fact be warmer. Okay, and that's what we're going here. So here we go. Albedo would still exist without an atmosphere, right? The moon has an albedo, right? Comets are made of ice. They have albedo that's almost 1, and they don't have an atmosphere. Pluto has a pretty darn high albedo, and it is too small to have an atmosphere. So if you take away the atmosphere, we would still have albedo. So the primary way that the atmosphere is going to affect our climate is not through albedo. Albedo is super important, but it's not the main thing that the atmosphere does. So that's this: remove the atmosphere and the albedo goes with it. No, it's just not. Hey, Isaiah, man, you're welcome to hang out, but like, if you're just gonna like preach in the chat, like, I'm not really interested in that. So let me do something really fast. I'm going to open that link in a new tab that you guys can't see. Okay. Doing this. And okay, now I'm going to like mute myself I opened up YouTube. Okay, cool. I forgot who I had made mods, and I can't see that from StreamYards, so I checked it on YouTube. So yeah, mods, if like, again, Isaiah, you're welcome to hang out, but if he's getting super annoying, like, mods, feel free to use your power. Anywho, I don't want to just like strictly ban people, because I'm here for exchanges of ideas, right? But if they're being like rude or just spamming, then go ahead. Anywho. Okay. So hopefully we see why this like so the moon, okay, the moon, and much like the moon and Mercury, with an albedo of 10%, with 20% more incoming like radiation on the hot side than the cold side. Yeah, so I'm not quite sure what that last bit is trying to say, but the naked Earth, right? The naked Earth would just be in radiative equilibrium with the sun, which would hold our temperature at about 0 degrees Fahrenheit. Mercury is warmer than us because it's closer to the sun, et cetera, so forth. Okay, so let's maybe move on to the second argument. The upwelling, trapped, absorbed, delayed, and the downwelling back radiated energy of the greenhouse gas loop must be first removed from the terrestrial system. I think what this is talking about is sunlight comes in, Earth absorbs it, and then the Earth is going to absorb that energy and re-emit it back to space. The hand motions are a required part. When that energy, so if there were no atmosphere, that energy would just go straight back out to space. And, you know, Marvin the Martian with his little telescope, that's why he could see us, right? Because, you know, that's why we can see other planets, because they're re-emitting light back to space. They don't make their own light, et cetera, so forth. But the Earth has an atmosphere, and so that atmosphere is able to interact with this energy that the Earth is pumping out. And it's not like magically making energy, it's absorbed it from the sun, and now it's re-emitting it, and now this re-emitted energy is going to interact with the atmosphere. If what that energy interacts with is like nitrogen dioxide, right? What, 78, 72, 70 something, percent of the atmosphere is made of, it just keeps on going. It doesn't interact, right? But some of it, when it interacts with specifically greenhouse gases like carbon dioxide, carbon monoxide, and methane, then that energy, as we saw with when we looked at the absorption spectrum, carbon dioxide is super good at absorbing in the infrared, in the range that the Earth spits out, but not at the range that the sun comes in. So the Earth's atmosphere, a way to think of it is effectively translucent to incoming solar radiation, but transparent to outgoing long wave radiation. So some of that energy that's coming up from the Earth is going to hit the atmosphere and interact with that, let's just say carbon dioxide, so I can only talk about one thing. Yeah, so it interacts with carbon dioxide. That carbon dioxide atom, it absorbs the incoming radiation. This is a type of nuclear reaction. So it absorbs that photon that has an energy in the infrared and then re-emits that energy in all directions. And that's the key point. So if it's going to re-emit in all directions, or you could also think of it re-emits in a random direction, and we've got a lot of CO2 atoms, right? So about half of the energy that the CO2 interacts with gets directed down, and about half gets directed up. So the half that gets directed up to space is part of that net outgoing radiation. Some of it goes back down to the Earth and adds to the heating of the Earth. Now, since this process has been going on for a really, really long time, we're in a nice equilibrium state, right? So let's see what he has to say about that. So the energy that gets like re-emitted from the CO2 back down to Earth is the trapped or delayed and the downwelling. Those are all ways to refer to that. And this must be first removed from the terrestrial system. If by removed you mean this is energy that would be emitted from the Earth anyway, that's fine. Removing this extra energy would shortchange and disrupt the balance at top of atmosphere. That's not true. That's not actually true. We can look at an energy balance diagram and I'll walk you guys through it. And TOA is top of atmosphere. So with some kind of, so this is saying that there has to be some extra energy that would violate laws of thermodynamics, LOT, law of thermodynamics, which first law, energy cannot be created or destroyed, blah, blah, blah. And so let's dig into this. Let's take a look at an energy balance. Now he sent me one. So let's first look at his. I'm a little concerned. So this number is accurate. Total surface heat loss. So is 168 watts per meter squared. That's true. Okay. So surface solar heat gain, it's not 168 watts per meter squared. Okay, so what this is trying to do is to account for all of the incoming and outgoing energy from the Earth system. So let me get like a better diagram for that. Animal agriculture absolutely contributes to greenhouse gases, specifically methane. So cow farts are heavily taxed in the United States because they contribute to methane. At zero pressure, and it would be like effectively no pressure, and at 0 degrees Fahrenheit, you're right, that's not a liquid, so that would just be ice. So that would increase Earth's albedo, making it colder, maybe. But again, that's not depending on the atmosphere, right? So albedo, the atmosphere can affect albedo mostly from clouds, but surface ice is the biggest contributor. Anywho, okay, so let's look for a proper Earth energy balance diagram. Okay, and I gotta switch which screen I'm sharing. Okay, share this button. Okay. Okay, so let's see. What's a good one? Yeah, I think this is a good one. Oh no, that's on Pin. It's gonna take me to Pinterest. That's not gonna go well. Uh, sure. Okay, this one's at least from like Stanford. That's probably a good source. Okay, open image in new tab. Okay. Okay. So incoming solar radiation, 342 watts per meter squared. For some reason, I thought that number was 168. Oh, that's what it is. Okay. So by the way, here's where he gets that absorbed by that 168 number from. That's how much is absorbed by the surface. That's not how much is coming in. So 342 watts per meter squared comes in from the sun. And then some of that, there's 77 watts per meter squared, is reflected by clouds, aerosols, and atmosphere. So that is that like reflection process. 168 makes it to the surface, with 30 being reflected by the surface. That's what's going to be reflected by. I guess I was wrong. I thought ice had a bigger effect than clouds, but it looks like globally clouds has a larger effect. I think about ice quite a bit. So 30 watts per meter squared gets reflected by the surface back out to space. So we lose 107 watts per meter squared. That's not like acting to heat anything. The 67 that's absorbed by the atmosphere, that is mostly, so ozone in the stratosphere, which is the layer of atmosphere above us. Ozone is really good at absorbing things in UV. So ozone in the stratosphere is actually great because it absorbs a lot of the harmful like radiation. So one of the issues where places with like low ozone, or one of the concerns with the ozone hole, is that if you actually lower ozone in the stratosphere, you don't want to breathe ozone, so you don't want it down here where we are, but in the stratosphere, it's a good thing to have. It helps reduce instances of skin cancer in humans because it's absorbing ultraviolet radiation, which is ionizing radiation, which is what causes damage to living things. So that's what that 67 number is mostly referring to. Okay, so then we get 168 watts per meter squared to the surface. Now we've got to deal with what's going to go out, right? So let's take a look at this. We should have one more down. Here we go. So what we've got to bring it back to this process. This is the process we're really interested in. So we're emitting 390 watts per meter squared from the surface. That is way too much, right? Because we only brought in 342, right? So how in the world are we emitting 390? Well, 350 of that, 40 is going to go straight out to space. 350 of that gets absorbed by greenhouse gases, and then 324 watts per meter squared gets absorbed back by the surface. So if we add up, I've got my calculator right here. We can do the math. We're going to take the 168 that makes it to the surface, plus the 324, what's reflected back down from greenhouse gases. That's 492. If you subtract out the 24 from thermals, and the 78 from evapotranspiration, which has to do with like how you transfer and lose energy, not lose, but like how you transfer energy with like water and when it changes phase and things like that. Anyway, that's left with exactly 390 watts per meter squared. I don't know if you can see my calculator, so you can believe me. My trusty TI. And that's the key here, is that all of these numbers should balance, right? Anywho, so then we get what is emitted to the atmosphere. So we have net outgoing long wave radiation at the top of atmosphere is 235. If we add that 235 to the 107 plus 107, that gets us 342, which is how we know that we are in a sort of equilibrium state with the Earth-Sun system. Our net incoming radiation is going to equal our net outgoing. Now, we have lots of processes going on here at the surface that moves it around, but we can move things around all we like down here, as long as eventually net in and net out is the same. So think of it like you are constantly pouring water, or you've got like a hose, right? And you're pouring water into your swimming pool. Okay, there is also a hole in the swimming pool, right? If people are swimming, right, they're mixing that water back and forth, up, down, splashing into the air, let it come back down. But as long as the rate that the hose is bringing water in is the same rate that water's leaking out of the hole, the level of the pool isn't going to change. And you can do whatever you like with it inside without magically having to add more water. So that's the same type of thing we're talking about, and why these greenhouse gas processes don't need extra energy or anything like that. So let's keep this picture in our heads, and then jump back to the energy diagram that we were sent, shall we? Application window, and then this button. Okay, so this total surface heat loss of 168, so that is surface, not top of atmosphere, and the difference between that matters, right? Oh, okay, so this is that back radiation. So this is the loop, right, of from clouds, right? We saw that on the diagram we just looked at. There's the like other things, yeah. Okay, so we don't, and this might be a key thing that this individual isn't understanding. Okay, so that the thing on Earth that's in equilibrium balance with the sun isn't the surface, it's the top of atmosphere. So top of atmosphere has to be in radiative equilibrium with the sun, but not the surface. If you didn't have an atmosphere, those would be the same thing, but we do have an atmosphere, so they're not the same thing. And so there's no law of thermodynamics problem with greenhouse gases, right? You don't have to make extra energy. You don't need extra energy from anywhere. It's just cycling it back down before it's allowed to escape, which adds to heat the Earth. Okay, so let's move on to leg 3. The extra upwelling, this is long wave infrared radiation, LWIR. And in atmospheric science, we generally use the shorthand of solar radiation we call shortwave, and radiation coming from the Earth we call long wave. It would be more accurate to say like ultraviolet or high energy for the incoming solar radiation, and infrared for the outgoing radiation from the Earth. But since in atmospheric science, we're really only dealing with one or the other, we just shorthand it by saying shortwave and long wave. Okay, this comes from an assumption that the Earth's surface radiates as an ideal black body. So that's not true. We know that there's no such thing as a true black body, right? Everything is shades of gray. That's why we include epsilon, which stands for emissivity, when we do calculations for top of atmosphere stuff. Epsilon is just how close is this object to an actual black body, right? If it was a 1, it'd be perfect. If it was a 0, it'd be like not a black body at all. Anyhow. Yes. Okay, so he's explaining emissivity, but we know what emissivity is. That's fine. Based on the non-radiative heat transfer participation of the contiguous atmospheric molecules. Okay, so this is non-radiant heat transfer. So this is if I have a warm layer of air and then a cold layer of air, right? This layer of air will warm this layer of air by conduction, the same way your tea kettle warms up, right? You just put a cold thing on a hot thing, and then the cold thing gets hot. That's conduction. Atmosphere does that too. And then the other process would be like boiling water. So that's convection. So this is hot and this is cold, but this is really hot, and so it rises and it starts a mechanical mixing process that also moves heat around. That is convection. So we're saying he's trying to say that conduction and convection, however, because of this is conduction and convection of of air molecules, got it. Radiation becomes accountable only for, okay, yeah, sure, total minus non-radiative. Okay, so heat transfer, right? The net heat being transferred is all of it, and all of it can be from radiative heat transfer and from not radiative heat transfer, right? We can divide it into two things. That's what he's doing here, which renders extra upwelling impossible. So I don't know why. So also radiative heat transfer rate is really only going to be important at top of atmosphere. I mean, I guess like any, well, okay, that's not true. So there's like electromagnetic energy can travel through a vacuum, right? Other types of energy can't. There are other ways that energy is transferred. Okay, so but why? I don't. Okay, emissivity is not. So he's saying that emissivity is just the radiative part of the heat transfer divided by the total heat being emitted. I think that's right. Actual. Okay. So, okay. In the case of the ubiquitous KT power flux balance graphic, that's fine. Emissivity is 0.16, or for the actual balance, emissivity is 0.39. There is no extra upwelling. Okay, so what he's saying is because the Earth isn't a perfect black body, because emissivity isn't 1, then greenhouse gases can't be real. I'm having a little is radioactive decay in the core significant here? No, because for atmospheric stuff, a wrong time scale is the short answer. Because the time it would take for the radioactive decay in the mantle to make it like to the crust is a really long time, whereas incoming solar radiation like immediately heats the surface, right? And even if we're talking about like the surface getting in balance, that's still not quite like geologic time scales. Okay. Okay, I'm glad I'm not the only one. I'm really having trouble understanding what he means, because there is no extra energy, right? It's just what's being moved around. Also, when you're talking about emissivity, you're talking about that black body balance, right? Black body radiation, and that has to do with top of the atmosphere, right? So the black body part, that calculation, or the gray body calculation where you include emissivity, doesn't care about anything that's going on below like the top of atmosphere. That's just at this level. So this argument doesn't make sense to me. But he did have a link to an experiment which apparently debunks the greenhouse gas theory with a boiling water pot. So that's interesting. Let me copy that link. I'll put it in my incognito window and maybe we can take a look at it. I'm not quite sure how a boiling pot of water is supposed to show me how carbon dioxide interacts with electromagnetic radiation of different wavelengths. I'm not quite sure how we're going to get there, but we'll try. We'll go on this journey together. Okay. Great. So this is, what website are we on? We're on Principal Scientific International with some nice capital Greek letter size. Okay. This feels very scientific. New experiment proves the greenhouse gas theory is bogus. Very scientific word. And thus there is zero scientific proof of man-made global warming. Okay. Radiative greenhouse gas effect theory. Cool. It insists that our planet radiates at a defined rate. Nope, that's not what that means. Okay, I'm not going to dig through this because it's just, it's a lot of nonsense. And yeah, I don't know. Do we want to suffer through it? Okay, let's see. Okay. This is a pretend conversation. Okay. So cool. So we've got a gallon of water boiling away with a nameplate rated 1500 watt heater at this altitude. Water properties has saturation temperature limited to 200 degrees Fahrenheit, and that's about what it's measured. Okay, the watt meter. Okay. Okay. I'm sorry, I should be reading more of this out loud. I don't want to have dead air, but I'm like cracking my head to the side. Okay. What I discovered of interest is increasing the area. This is why heat exchanger manufacturers add fins, increasing the radiative. It's not radiative surface area at that point, man, because it's talking about this is conduction. Nope. There is an area factor on the attached spreadsheet. If the area were tripled, radiations share emissivity. Let's put that away. Let's Google. Let's just Google emissivity because my brain is breaking at the moment. And what is emissivity and why is it important? That looks like a great. Okay. There we go. Brilliant. Okay. All objects at temperatures above absolute zero emit thermal radiation. Let's just accept the basic cookies. Oh my goodness, that button. Oh, but you're not going to remember it because I'm on incognito mode. Okay. Emissivity is defined as the ratio of the energy radiated from material's surface to that radiated from a perfect emitter. Yes, okay, all right, I'm not losing my mind. So his calculation for emissivity I don't think is right, because what you've got to do with emissivity, David, my debate was last Thursday, but you can watch the replay over on Modern Day Debate if you would like. Okay. So to actually find emissivity, you have to like measure the temperature coming off of a thing and then compare that to like the perfect emissivity, the nice, like there's a graph. It's like Stephen Boltzmann and all that jazz. So it's not like, cause like right this second, if you like took a thermal camera and measured the energy coming off of me, right? That's not radiating from like, you don't have to be like, but what about Maddie is conducting energy? Oh, I'm so sorry, dude. I think I announced it on Twitter, but I forgot to do it on my community page. Yeah, and then yeah, but it's over on Modern Day Debate. And then if you want, I went on Dapper Dino's channel afterwards and we did an after show. It was very fun. So if you want some good entertainment. Okay. Anywho, seeing the debate about like ethical like environmentalism and farming practices. That's a good conversation going on in the chat. Okay. So yeah, so if you measure the heat coming off of me, like you're not measuring, like if you took a thermal camera to me, right, I'm emitting heat. And that's my emissivity. It's not about is the heat being removed from my body by radiation or conduction or convection? Like by golly, I hope it's mostly conduction, right? Otherwise we've got a problem. And so it's not about how that heat is being removed, it's about how much I'm emitting, right? That's what emissivity measures. So this idea that like you have to take so I'm not really sure what he was trying to prove with his like kettle experiment. Yeah. I hope that makes sense. Okay, so cool. Chat, what do you guys think? Did I successfully go over the arguments? I feel like I did. I feel like it's really one root argument, which is the argument that the atmosphere, like one, that greenhouse gases requires like an extra magical input of energy, which it doesn't. If you just move it around, you can warm the surface. And then two, not understanding like the role the atmosphere plays. So wanting to use only like sort of the optics, right? Because you can get albedo from just like that's like optics physics, not like nuclear physics, right? But you've got to consider that like absorption, and we took a look at how different gases absorb at different wavelengths and all that jazz. And yeah, okay. I think I'm done with that. I think I'm done with that debate. Those points. So, anywho, now I can just point to this video if they post that same block of comments again. Yeah. Okay. So chat, how are you guys doing? I was planning on streaming for about an hour. We're at about the hour mark. Unless y'all have any questions or anything I can answer for you. Dapper, by the way, I did spill the beans that our D&D game is going to start streaming here in a couple weeks, and I'm very excited. Okay, well, team, I think I will let you all go then. Everybody have a great night. And on Sunday, it'll be a premiere, not a live stream, but I'll try to be in chat for the premiere if I'm not yelling at my Python code to just make the plot already. Okay, so everybody have a good night. I'm going to go back to being a unicorn, and I'll see you guys soon. Okay, bye, team.